Okay, so let's begin. Right, this is the introduction to statistics. So one of the things about statistics is it's an applied branch of mathematics, which is just a fancy way of saying that you'll use it a lot more in real life than you probably will algebra. Statistics deals with information. And the kinds of things it does is, how do you collect information? How do you summarize information? And how do you make inferences, which are just fancy names for conclusions or predictions of what is going on based on that data? And a lot of people see statistics in their jobs. Any kind of job that's based on data-driven decisions is going to have in the back of that the concepts of statistics. So I'm going to start off with what you would do first in statistics is you would collect the data. Well, what kind of data do you collect? Almost anything. Anything that's information is data. That's all it is. But the two major kinds of data, and I'm not using the jargon terms, you can look at them in the book, is numerical data, and then I'll call it non-numerical. Well, that's a pretty big dichotomy. You're either a number or you ain't a number, right? Now, non-numerical, it's got all sorts of names. So the jargon would be categorical data. I've heard it called, oh, what is that one? I'm trying to, you have qualitative data. Right. Now, it just means it's not numbers. So what falls into this branch? Well, you ask someone what their favorite color is, and yes, color has a unit. And you ask people who they're going to vote for, Republican, Green Party, Royalists, whatever it might be. You could say, what kind of car have you got? And all sorts of data that isn't numbers, right? It's categorical data. Now, over on this side, you have numerical data. So numerical data could be your age, how much money you've got, your height, your weight, I don't know, number of children. Yeah, so you can imagine what that data is like. Now, since there is two major types of data, we have to deal with them in two different ways. I'll give you a simple example. One of the things that you can do to numerical data is you can summarize it by giving a single number that represents a typical person in that group. Now that single number is very often, in layman's terms, is called the average, right? So the average age of people in your family, or the average age of an American, or whatever. It's really could be either one of these two, because they are different. The mean is the one you're typically used to. So suppose you had a class of 20 people and you wanted to know what their average age was, right? Well, you take the youngest all the way up to the oldest, right? You add them all up and you divide by 20, and let's just pretend that I got that answer. And it's 21, which used to be the age of my sister and actually was her age for about 10 years. You didn't catch that one, did you? So the typical person in this class could be 21 years old. Now that doesn't mean everybody is 21, right? It's a bit like if you lined them all up, roughly in the middle, they'd be about 21. That's what you use when you add up everybody's age, right? And you divide by how many there are. There is another measurement for the typical person in the middle. And it's a median. And the medians, perhaps in this class, could be 20. Now, to calculate the median, you imagine everybody in the class from the youngest on the left to the oldest on the right, and you walked down the row until you got to the middle of the line, and you said to the person who's in the middle, how old are you? And they said, I'm 20. Now you might think, why are they not the same? Well, could you imagine you could have a class, this would be a silly class, but 19 of the class were all 20 years old. And one of them was 95 years old. Do you know that the mean of that class would be in their 30s? Roughly. But if you did the median, wouldn't that person in the middle be one of those 20-year-olds? And so there are ways of choosing the middle person. Well, let's look at the non-numerical, right? The stuff that ain't numbers. You can't find the mean because it has no meaning. Suppose you had people and the answer to what was your favourite colour ended up being that they only chose 3 because they had no imagination. And you had, that is the result. What's the average colour? See, it doesn't make sense. I mean, you can't get 17 buckets of red paint, 13 buckets of blue paint, and 13 buckets of green paint, chuck them in a really big oil drum, give them a good stir, and say, it looks a kind of reddish, bluish, greenish colour. And that was the average colour for everyone. You see, it makes no sense. Right? So you cannot talk about means and measures of average. You can't look at the types of cars people get and say the average car is somewhere between a Volkswagen and a Ford Capri, right? The order can be changed as well, which makes them quite different. So this is just a big picture thing, right? So you collect the data, you know it's numerical or non-numerical, and what you can do with it is quite different. The types of diagrams that you can use on the data can very often be different. When it's numbers, you would use histograms, whereas if it was non-numerical, you'd probably use bar graphs. And you'll get into seeing things like that. So why do people collect data? Well, you could just do it because you feel like you want to, but most people collect data because there's a question to be answered. So someone out there poses a question. Let's just suppose someone comes up and says, hey, there's this new drug which we think's really good at reducing the amount of time people spend in hospital with the COVID virus. Well, your question would be, is that true? Well, how would you be able to test that? You can't just do, well, my Aunt Janice had it, and she took this new drug, and she was out in 3 days, right? And my Uncle George, he didn't get the drug, and he was in at the same time as her, and he took 8 days before he got out. See that new drug? It works. Well, that's called anecdotal evidence, and anecdotal evidence is extremely bad evidence. Because couldn't your Uncle George, or whatever I called him, couldn't he be really sick? And his aunt, she was a pretty healthy one, right? So could you see that the reason she got out earlier, she was healthy and she got a minor version, and poor uncle, he was a bit older, a bit slower, a bit weaker. It took him longer. So it was nothing to do with the drug, it was just coincidence. So you want to collect that information, you have to set up an experiment. And they're doing that right now with most of the drug treatments that are valid ones, right? And what you do is you get a group of 1,000 people, say. Bigger the better, right? If you do an experiment with 4 people, it's kind of risky, isn't it? You could just get bad data, right? So you do it 1,000. And you ask, well, you don't so much ask them, but you split them into 2 groups. And one group get the new drug, whatever that drug is, right? And the other group get the usual drugs, whatever those are. And then you can compare the 2 groups' results. What's the average amount of time that someone took to recover in the group that got the new drug? What was the average amount of time it took those who got the usual drugs? And then if there's any distinguishing differences, then you can say, yeah, that new drug's doing a better job, or no, it's doing the same, ain't making much difference. Or if you're really unlucky, stop giving them that drug. It's making it worse, not better. Right? You can imagine a situation where the average time of the people who got the new drug was much longer. And we're going to be looking, as we go through this course, how to look at whatever the question is being asked, how to look at the data and come up with a systematic way of approaching the big question. Is there evidence to support whatever that question is? Now, it could be supporting it by saying it's true, but it can also be it's not true, right? Either conclusion is possible. I'll give you another example of that. I've used it before, but it's one I kind of like. We get bombarded, especially in today's environment, with people telling us facts, inverted commas, and saying it in a way that sounds reasonable, and they give you information to back it up. And I want you to, hopefully by the time you finish this course, to have a little bit more skepticism about that way of looking at things. So I've got a little story for you to kind of emphasize how that works. It's a made-up story. Suppose a Seattle newspaper puts out an article and it says, Seattle police force is racist. Only 10% of Seattle's police force are Scottish. That's a tiny number. See, they don't like Scottish people. They're racist against us. Right, so well, they said it, and they backed up with a fact. The fact is 10% of Seattle police force are Scottish. Right? That's superficial. That's a headline that they run with. There's a piece of information that's missing from that actually helps you decide the truth to that statement. Does anyone get an idea of what that extra piece of information that could help you decide whether or not Seattle police force having 10% was a racist thing?
It would be the population of Scottish people in Seattle, right?
Exactly. Suppose Seattle, 10% of Seattle people were Scottish. Shouldn't 10% of the police force be Scottish be a very reasonable percentage to expect? Right? 10% of the population in Seattle, 10% of them are in the police force. That's fine. So that would be evidence, nothing special. Suppose 50% of Seattle was Scottish. 50%. But only 10% in the police force. Do you see that piece of evidence is saying, look, that's not right. Half of Seattle are Scottish. Why aren't half the police force Scottish, right? Why are they not higher in the same proportion as the place that they're policing? You see that? Suppose 1% of Scottish is Seattle. 10% of the police force are. Do you see that's actually evidence of favouritism amongst the Scottish population? So I like to joke, why are so many Boston policemen Irish? Right? Percentage of the population. Or is it Irish people get into the police force and Irish people like hiring Irish people? And that's why there's more and more of them than there should be of any other particular racial group or ethnic group. You see how that can work? So when you're asking a question, you need to collect good data. Here's a different problem with collecting good data. Do you know if I talk to you and I ask you a question, I can ask it in a way that I can get the response I want, or at least improve the chances that I get the response I want. So how about, here's a pretend question. Suppose I was doing a poll out there and I asked a random selection of people, are you in favour of getting all student loans paid off by the government? Now, if I ask it in that way, yeah, sounds like a good deal to me. My wife's got a big student loan. I'd love that to get paid off by the government. Yeah, go for it. So, newspaper article, 80% of Americans are in favor of student loans being paid by the government. Suppose I take that same piece, that same question and say to you, are you in favor of student loans being paid by increasing your income tax? What do you think is going to happen to the number of people who say yes now? What do you think?
Wouldn't be as popular.
Wouldn't be as popular. If you phrase a question in a particular way, you see the same essential question, do you like student loans being paid off? Kind of a different answer. It's not uncommon for people to phrase a question in such a way that they get the response that they're trying to get. Take abortion. That's my last example of this biased way of asking. I could say to you, are you in favor of a woman's right to choose to have an abortion or not? Or I could ask, do you think it's right that a woman is allowed to kill her unborn child? Can you see the way I phrased those questions are blatant, well, certainly the last one was, right, are blatantly trying to influence your answer. And so when people ask questions, even that can cause problems. So you have to ask unbiased, simply just say, are you in favor of abortion, right? Don't influence it anyway, and you're more likely to get a true answer. Okay, that's my little intro bit over the general stuff. We have lots of things that we're going to be doing in the future, but that's for the future. Let's get started. Any homework questions or concepts that you're having issues with that we could talk about now?
I've got one if no one else does.
Okay, that's a good start. What you got for me?
Right, so I was looking at the videos from the other professor that you had up, and he said something that I couldn't quite wrap my head around, and maybe you can explain it. We was giving the let's make a deal scenario where.
I haven't actually. Yeah, sorry, I haven't seen them. But keep going. The concept might be something I know about.
Well, so he basically said. Yeah, you might want to see it because I don't know if I could explain it quite as well. But he said, you have 3 doors to choose from. Mm-hmm. You pick door number 1, so they reveal that door number 2 was the booby prize.
Right.
And then he suggested that by changing your choice at that point, you actually increase your odds. But it didn't make sense to me because door number 2 was no longer a choice. I don't know if anybody else watched this or if this is totally gibberish to everybody else. You can answer that question later.
I do know that the concept of that. Okay, here goes. Imagine that you're at the start of the competition and there's that guy there, which is number 2. You don't know it right now, but number 2 is the booby prize, right? And one of these is the big one, and one of these is the small one. I think the big one's a car or something, right? And the small one's a hamper of food or whatever, right? So what's your probability then of winning the big car? Right now, it's 1 out of 3, isn't it?
Yes.
Right.
Right. And then the story developed, and you picked box number 1. Right, that's when you picked the big one. I better not put that there. Right. Now, they tell you, well done, because number 2 is the booby prize, so you don't pick that one, right? Now, what's your chances of winning the big prize now? Well, if you keep in, pretend you don't know which it is, right? Isn't it now a 1 in 2 chance that you pick the big one?
Yeah.
Right. So before you chose, you had a 1 in 3 chance of getting the car. After you made your choice, whatever that happens to be, you've now got that one. So why is there a change in the probabilities of getting the big car? The part about switching is not so important. It's more to do with the fact that the probability has now changed given a piece of extra information. The piece of extra information is that door number 2 had the booby prize. There is something already that's changed that you haven't taken account of. Suppose you'd picked door number 2 right at the start, wouldn't the competition be over?
Right.
Yeah.
So what has changed? What has changed is you picked a door that wasn't the booby prize. So this story has now changed from that one. So your probability of winning a good win has now increased from 33.33% up to 50%. A very complicated version of that same idea is a thing they called card counting. So in Vegas, if you play blackjack, one of the things that are important in blackjack are, let's say you're playing with 3 decks, is how many aces are still in the deck and how many of the face cards like kings, queens and jacks. And as the game progresses, don't aces and jacks and kings get played? So the first hand happens, second hand happens, maybe the third and fourth hand has happened. And maybe a quarter of the cards have now been played and you've been paying very special attention to what those cards are. So you're now in deal number 10. The cards that are left are not the same as you would have had at the beginning when there was 4 decks with 4 aces times 4, 16 aces, right? Let's pretend it's been a really bad day or good day for aces. 12 of those aces are already gone. Do you see there are only 4 aces left, but there's a lot more cards? Do you see your chances of that next one being an ace is quite low? They change through time. So something happens that changes, the probabilities of the event. Now, the trick in the card counting situation is that the rules of cards, the rules of blackjack are based on the fact that you pretend that it's a full deck of cards and it's the first deal. And so there's 4 of every card that you could possibly think of. And so you can buy little cards that says, if you've got 17, stick, if you've got 14, take a draw, and, depending what the dealer's got. And they've got a whole load of a little card with a little, this is what you do if this happens. Well, that card only works on the first deal of the first deck. But by the time you've got to halfway through the deck before they stop, lots of different things could have happened. And depending if you've counted them and kept track of them, you could calculate or recalculate the probabilities of you winning if you take another card or whatever. It's not actually illegal, but it's not allowed. So if they catch you doing it, they will boot you out and you won't get to play in casinos anymore. So I don't know if that's fully answered your question, but why I chose 1 or 3, that's just a subtlety of the thing. The major difference is that something has happened that has changed the probability. If you're interested, that comes up in a section that's called conditional probability. If you look in the textbook, you can look ahead to see what that is. Okay, have we got another question? Doesn't need to be a physical question. It could just be a question on a concept or an idea. Can't get one, I'm going to pick something. Okay. Here's some data. And it's in the form of a table. Now, this table is using some categorical data, right? Your favorite color. In this sex, we have a code where male 1 means it's a male and 0 means it's a female. So the way you would read this information is that first person is a male and they liked red. That second person is a female and she liked blue. When you see data written this way, do you know what the jargon term for that data is?
Category variables.
These are definitely categorical variables. The way that this information is described has a special name.
Is it stackable data?
Yes, that's the word I was looking for. So as you're going through this textbook, you're going to come up with lots of jargon words. Right? This information is in one big stack, so it's stackable information. It could have been written this way. And so on. Now, when I write it this way, do you see that there are two columns? One that says male, female, male, female, and the second column had red boots. So I guess there might be a heading to this, which would be sex and color, right? And you see this categorical data is made up of everybody kind of grouped together, but males with red, females, and so on, right? Now, this data very often gets split into two tables. And in the males, you just say red and blue, whatever they said. And in the female group, you say blue, red, and whatever they say. This table, this one, and these two together, aren't they telling you the same information? It's the structure that they put, the way they group the data, the way they put it together is the difference. And when we talk about categorical data like this, for instance, there are two variables, as someone mentioned. And in this case, the variable would be the sex of the person and the color that they chose. Is that okay? Have you got that kind of, the difference in the way that's kind of working out? Oh. Right. Here's a little example of an issue between numerical and non-numerical. So we'll call it categorical, which I believe is the word they use here. Right, in this textbook, what word do they use when they talk about numerical data? Do they have a special name for that kind of data?
No, it was both categorical and or qualitative.
Right, so quantitative or qualitative. Right, so this would be quantitative.
Quantitative.
Yeah, it sounds very similar to this one, doesn't it? Okay, now, if I said to you, you collected data on the ages of people, that would definitely belong in this camp, agreed? You're 42, you're 77, you're 12, right? If I said, what's your favorite color? It's definitely in that. But there are some this is a very special case, but it's a nuance that's interesting. There is certain data that sounds numerical, but belongs in the qualitative. Give you an example of two of them. Your telephone number and your social security number. Now, if someone says, what's your telephone number, right? It's 360-123-456, right? Numbers. So why doesn't it count as, numbers? Why doesn't it belong in that camp? The reason it doesn't is because,
It is categories, coding.
yeah, it's a code. Social Security is just a code, right? Every person gets a unique Social Security number. For instance, in Britain, we have what's called a national insurance number, which is essentially the same function, but ours have letters in them, right? So this isn't mine, I'm making this up, right? But a national insurance number in Scotland might be AB 42C17. Now, when you see it that way, you're immediately going to say, hey, that's not really a number. There's C's and W's and A's in it, right? You can see it as a code. So how do you distinguish between real numbers and codes that really belong in the categorical side? What I do is I say to myself, imagine I got 10 people's telephone numbers and I averaged them out. Would the average telephone number have any meaning?
No.
No.
No. That's because it's a code. If you got 10 people's, random people's Social Security numbers, wouldn't the average that you got from that mean nothing? Yeah, your average Social Security number is 542,312.6. It means nothing, right? Your average telephone number is 125,551.3, right? Doesn't mean anything. So just in case you come across a couple of situations where they give you a piece of data and they ask you, which camp does it fall under? And my test for that is, imagine you collected 10 of these things and you average them out. Would that average have any meaning? Off the top of my head then, do you know the numbers on football players' backs? Suppose you randomly got 10 football players and you averaged the numbers on their back. Would that actually have any meaning? No,
No.
because it's a code, right? It counts as categorical data. So if you were doing telephone numbers, what could you do? Well, I guess you could collect lots of people's telephone numbers and then group them according to the first 3 digits. Right, all the telephone numbers that had 360 at the beginning and count them as one group and all the others had whatever is the next one. But there's not an awful lot you can do to that kind of data. Really, it's quite superficial what you can do to categorical data. You can kind of count how many of each there is, and you can make some pretty pictures occasionally, and that's about it. Almost all the work that we do in statistics comes from the numerical side, right? Where the data is really numbers, right? And that you can manipulate those numbers and come up with things that actually do have a meaning behind them, right? The average age of this class does have a meaning, right? For instance, suppose I told you I have 2 statistics classes, which I don't, but I have. And they're both the same size, right? They're both got 20 students. But this class, the average age is 21. And the other class, the average age is 61. Now, you don't know anything else about that other class, except there's 20 of them, and their average age is 61. But wouldn't it be a reasonable conclusion that the second class probably has a lot more older students in it than this one has?
Yeah.
Right? You don't know the specific numbers, but the conclusion is still valid, right? Now, suppose the other class is exactly the same average as this class, 21. I think the conclusion that you can make is a little vaguer here. Both classes are probably kind of similar in age distribution, right? They're about 21 in the middle, but you know, you're going to get 16-year-olds, you're going to get 40-year-olds, but they're probably going to be roughly about the same distribution. That would maybe be a reasonable conclusion, but it's a lot less strong. I can imagine all sorts of weird combinations. Can you imagine a class where the average age was 21 and it consisted of 18 students that were all 21 and a 5-year-old and a 37-year-old? That would average out at 21 as well, wouldn't it? Or you could have a class full of everybody being 21. Or a class of half of them 20 and half of them 22. Do you see that you can get 21 lots of different ways, can't you? So you can't say that both classes are identical. You can just say that they're roughly about the same, very roughly. We get any more questions?
I have questions, sir.
Go for it. What you got?
It's under section 1.4 actually. So the example problem is assume that in a certain region there will be a need for 108,728 personal care aides in 2024, a growth of about 23% over 2014 levels. How many personal care aides were there in region in 2014? So what I did, sir, this one I'm having a problem regarding the finding the portion or the percentage. But when I tried to do the help questions under that questions, it says that divide the known size of this portion by the decimal equivalent of the percentage. So what I did is I have a formula here based on the help question. I will show it to you, sir. Hold on.
Oh, okay.
I'm writing it down.
If you stick it up on the screen, I'll hopefully be able to read it.
I'll try to, I don't know how to do it, but
Yeah, just do what you just did and keep it there for a few seconds.
okay, hold on. So what I did is I tried to find the variable, variable x, like this.
Okay.
Did you see it, sir?
Yeah.
Oh, I tried to mirror it. So what I
Okay.
did is 1 plus, and then the decimal of the percentage of 23%, which is 0.23, and then I will, so the variable x is the personal care total population of personal care aides in 2014. So I'm looking for that x, so I have to divide it both sides to get the value of the x.
Correct. That
So-
sounds reasonable.
Yeah, so but I have questions regarding why there is one.
Oh, okay.
Yeah, so that's my question.
Okay. So if you do that, you get the right answer. But your question is, where did this weird one come from?
Yeah,
I
yeah.
now have it. Okay. Let's get this out of the way so it's not a distraction. So if you start off with x, whatever x is,
Mhm.
and then you add 23% of it, it's adding 0.23, which is 23% of a decimal of x, so 0.23x. So that's the start plus 23% more of the start. Now, if you'll notice that these both have x's, if you take out the x as a common factor, can you see the 1 and where it now comes from?
Mm.
What you started with plus 23% more of what you started with is equal to, and all I've done is taken out this as a common factor. So if you take out x as a common factor from here, you get 1. If you take out x as a common factor from here, you get the 0.23, and that's where that came from.
Okay.
You could actually totally bypass that by just adding them together and calling it 1.23x right off the bat,
Yeah.
which is what it would be.
Is that following the rule then, that because anytime we see x is x, there's always that coefficient of 1 that isn't written? Is that
Correct. That's it. So technically, we never write it, but it's 1x
Okay.
plus 0.23x. Pull out those, and you've got 1 plus 0.23x. Now,
right? Okay.
that's where this came from. It has to equal this. So you divide both sides by 1.23, and whatever weird decimal you get, that is your answer. Now, I believe these questions are set up so they go random on you. So even if you went back and looked at that particular question, it may not be 108,000, it may be 122,000, and it may not be a 23% growth, but put that out of the way because I wasn't sure your question.
So,
You know, the next time it might be 12% growth. So whenever we do a question, you have to adapt it to the circumstances of the numbers being used in your question, which isn't always the same. You know, so even if you phone up, you know, James and say, I'm on this question, they're probably not going to be seeing the same numbers as you, and therefore it's a bit hard for you to check with each other in that way.
yeah, but you have to, so when you encounter this kind of questions,
Mm-hmm.
it's automatic that the formula is going to be like you have to plus like X.
Yes,
plus.
that part will be the same. It's just, it might not be 0.23. Someday it might be 12%, so it'll be 0.12 for them. And this number here may not be the same. But essentially the process will be the same, right? What you do will be the same. You'll just do it with perhaps different numbers.
How do you know when you're going to be prompt to put the 1 in front of there?
Yeah, that's a big follow-up.
Right. Well, as far as the story, the way I picked it up, it goes something like this, that they started off with this amount, and then it grew by 23%, right? And we're trying to find out what this imaginary number that when you added 23% of it gave me that. So I'm saying to myself, okay, what do I know? Well, I know I started off with something, and then it increased by 23. And what did I end up with? I ended up with this number. Right. Let's pretend it was a different story. You started with some stuff and it reduced by 42%, right? It went down by 42%. So I'd say, okay, I started off with some stuff and it went down by 42%. And I got whatever the number in the story was. So do you see that this would be a growth or an increase situation, and this story would be a decrease? So we're looking for a story where there's a start amount that you don't know. You know what it finished up as, and you're told that it started off as some unknown number and it increased by 23%, or it started off in my second example here as some number, but it reduced by, say, 42%. So the questions are phrased in a very specific way. There's something you don't know that's either increased or decreased by a certain percent, and all you are told is what the final result after all of that is. Right? That makes sense. So,
well, I just a question on that. So this scenario is a little bit different because I had a challenge with the same one. But
right.
So you're starting off with a known, and you're giving that a percent of growth for the unknown. So it's still a additional.
Yes.
It's still the same process.
Right. So the key word here is growth would mean you'd be adding 0.23x. If it reduced by 10%, you'd subtract 0.1x. Now, I'm going to have to leave at this point. So if there's any last minute questions, this meeting is going to be recorded and put in Zoom. I'll do some editing with the bits that really weren't particularly necessary for us to record. And you can go back and maybe look over some of the answers if you didn't kind of catch the gist of what I was saying. Obviously, feel free to shoot me an email at any time. If I can answer it with email, I'll do that. If not, I'll do a Zoom meeting and we'll do a little screen like this, and I'll just take you, walk you through whatever the homework question is that you're having issues with. At the end of this particular week, Sunday, there is I believe there's I can't remember what its name is. It's called a quiz of some kind, isn't it? Quiz 1 or something. Review, quiz, whatever. You're just going to do those the best you can. Make sure that you are really careful about putting the answers in, but next week, at the end of week 2, we're going to have a more formal test. And what's going to happen there is that you're going to have to upload your working. So write down your working. You're going to take pictures of it using, hopefully you've tried out the CAM scanner. And you'll send it to me in Canvas by dropping it into an upload box that we'll have set up. And I'll be doing that because in a lot of these questions, all the computer will say is you're right or you're wrong, and that's it. But for the questions, especially the questions that you're wrong, if I get to see your working, I can still give you partial credit, and that's worth it. Because take that last question. Maybe the only thing you got wrong is you decided that you were going to take away 0.23%, right? So it's 1x, take away 0.2, but you did everything else right, right? You'd still get half the points rather than 0. It also allows me to check that you're not cheating, because if I don't see working, I'm not going to give you anything for those questions. So you need to make sure that you write down anything that's relevant to each question. And any last minute questions before we leave?
Sir, regarding the assignment that posted on Canvas, the one that you're talking about, so are you going to post the questions on Canvas and then
No. They will still be on your MathLab, just usual online questions. All that the Canvas is going to be used for is a placeholder that you will upload your copies of your working to that folder. So make sure when you do that, you put them as a PDF, right? And CAM Scanner will do that for you, but put them as a PDF, and then it would be nice if you said Manuel Smith, making some names up here, right? Math 146, you know, test 1. Because I'm going to get about 120 of these, and it's much easier if I know who you are, and I can categorize you that way. Does that make sense? Have you ever uploaded anything to Canvas? Simply, you just go in to the shell that I'll have there. You'll hit the upload. You'll have your file on your desktop or whatever it is. You'll click on that one. That's the one it'll pick. It'll send it to that location, and then I can go and look at it. Right. If you're not sure about how to do that, why don't you use that little shell I've put up right now as a practice? Just make a practice PDF that says, "Hi, this is me," and upload it. And I will go in from time to time and I say, "Yep, Janice, that's how you do it. It's working." I'll give you an idea, because you don't want to wait till 11:50 on the Sunday, because that's typically when you'll be finished it, and then say, "It ain't working. I don't know how to make it work. What am I doing?" Right? We don't want that situation. So feel free to do a little dummy run on it, and if it works out, then you know you're good to go when a week on Sunday happens. This week, nothing. This week, you're just doing your normal thing online, and you get what you get. But next week, at the end of week 2, we do have a test where that's going to become much more important.
Just a quick question on my lab. Just say hypothetically, we don't get everything done on Sunday night.
You get what you get.
Will you still have access to the work to be able to practice?
No, it'll be gone.
Okay.
So you got to do it when it's there.
Fair enough.
What you can do instead is, if you look at your textbook has other examples there, and they do have solutions to the odd numbers at the back. So it's not that you won't have access to chapter 1 stuff, you just won't have access to chapter 1 online homework. Everything else, you can go there and you can do some more practice there. But remember, homework's graded, and it's part of your grade, so it's 30% of your grade. So yeah, don't procrastinate. There's lots of questions, so there might be a question you're stuck on. It's okay to ask me. Shoot me an email. Don't shoot me an email at 11:50 on Sunday night, because I probably won't be there. But you know, give me some time to reply. And you can leave a question out and come back to it. I believe that's possible in this, isn't it? I mean, I'm sure you're getting in and out all the time in your homework. Yeah. So if you're having real hassle with 15, rather than spend 20 minutes or half an hour, yeah, shoot me an email and we'll fix it. Okay. But as I say, and I really do have to go, because I have 5 minutes to start another meeting. And it was nice seeing you all. And we are, one last thing. What have I got? Let's check I got it. Yeah, just hold on 2 seconds. Perfect. I'm just leaving this screen for a second because this is everybody that's here, so I can give you your participation point for week 1. Right, so I'm just leaving it here for a few seconds more on the video, and we are definitely bye. Have a nice day, and I'll see you class meeting or officer, whatever. We're out of here.